Yeah, I think there's an overwhelming desire within the MIT environment to not only do research, but do research that makes a really big difference. I think everyone has their eye on some problem that is not small scale. It's always very global in scope. And so the sort of the excitement of working within that environment has certainly helped drive the application of this research into industry where it really makes the biggest difference. And so Dave and I were both able to gain some entrepreneurial experience within the MIT environment. I was co-founder of another coatings company back in 2012 and sort of was able to cut my teeth on assessing markets and opportunities and business development. And the extent to which MIT fosters the entrepreneurial environment, especially with these more difficult materials endeavors, has been a huge, huge help.
And I would also add that Professors Gleason and Varanasi are especially in tune with trying to find industrially relevant applications. So Professor Varanasi comes from 5 years of research at GE Global Research Center, and Professor Gleason has many different industry collaborations. She's also spun out another company of her own.
We're excited to work together with the ILP and other organizations to really help foster the energy, materials, and heavy tech startups. We certainly benefit from having the intense brain power of both professors and also the potential employee pool within the MIT ecosystem within a 10-minute walk. At the early outset of my PhD research, I was looking at some very intricate, very complex coatings and surfaces to boost the performance of the heat exchange surfaces in these applications as much as possible. But eventually, after taking more of a look towards the application and the industrial relevance of these coatings, realized that the performance was reaching a point of limited gains. And what was really needed was a simple, highly manufacturable solution to these heat exchange problems. And so that led us to pursue the development of these coatings that are very robust and very capable of being applied to large areas, which is important for these heat exchange applications.
Professor Gleason basically invented this form of chemical vapor deposition, this ICVD technique. It's been essentially under development for the past 15 years or so, starting from inorganic CVD, a hot wire filament CVD of diamond. So going from inorganics to organic materials, and the motivation being that you want to be able to deposit these polymers using a chemical vapor deposition technique, but not subject your substrates to very high temperatures. And so by using these hot filaments, you're actually able to keep your substrate at room temperature, but be able to deposit polymers from this vapor phase precursors. And so the technique itself is extremely versatile. You can get many different functionalities just by changing the precursor that you put into it. So Professor Gleason has explored this ICVD technique for many different applications.
So we started with this process and really honed in on a specific chemistry that was optimized for steam condensers, which has been an outstanding problem for the better part of a century, getting the films of liquid that build up on steam condensers and block the flow of heat, getting these films broken up and shed from that surface as rapidly as possible. So that means optimizing not just, of course, the durability of the coating, but also the wettability in the presence of steam. So we identified a certain formulation and then subjected it to testing within essentially a miniature power plant that we had built within the Varanasi lab to simulate the conditions, the pressures and temperatures that you would experience inside an actual operating power plant. And the endurance data that we were able to obtain from the apparatus has been extremely useful in accelerating the business development and really giving the technology the legs and the validation that is needed to go forward.
Applying this to power plant condensers can significantly increase the efficiency of these condensers, which increases the efficiency of the power generation cycle, which in turn lowers emissions, lowers water usage. So applied globally, this could have a huge impact on CO2 emissions.
So for a typical large-scale power plant that implements this coating, the amount of CO2 it would be offsetting is equivalent to a few thousand cars, and that's just a single plant. And with this process, you can use essentially a big truck with some deposition equipment to retrofit these plants, and it can be driving to a new plant every week. And so with a handful of these trucks, you can have a bigger impact on CO2 than the entire solar industry installed last year. So really the personal motivations behind this were realizing that, heck, with a handful of really smart people, we can have more impact than entire global industries have.